Okay, now this is a typical kind of flowchart that's asked in scholarship. One of the things to keep in mind is that the ones in NCA can be difficult at times, and you may have to work backwards from information. But in scholarship, you really have to consider extra pieces of information, and you may have to rethink some of the structures that you've drawn. So for a start, this is just, as I said, identifying A through F. And we're given information such as first A's can only exist as enantiomers, so we've got the 4 different groups attached to a central or chiral carbon, or it doesn't have to be central, but asymmetrical or chiral carbon. B does not react with toluenes or phthalings, so it can't be an aldehyde, in other words. D and E cannot exist as geometric isomers, so there must be a double bond there, but they wouldn't perhaps have, they would, if they had the same groups on one of the carbons with a double bond, that would mean it can't exist as a geometric isomer. And E reacts with HCl to produce compound F as a major product and also to regenerate C. So C and F are basically structural isomers. They're very, maybe we're talking about a major and minor product there. So when we look at this flowchart, one of the things that there are certain obvious things. For start, obviously SOCl2 means that this here has got to be an alcohol. It could have been a, if there was 2 O's there, would probably be looking at a carboxylic acid. But remembering SOCl2, PCl3 and PCl5, what they do is, if you've got a C with an OH, it'll substitute that, whether that C has an OH and a double bond, so whether it's carboxylic acid or just an alcohol, it'll basically swap out that OH group in each case. Now in this one it's also telling us that it gets oxidized, that's what dichromate is obviously, and it gets oxidized to a product B that doesn't react with toluenes or phthalings. And if it's not going to produce an aldehyde at all, then it means it's probably a secondary alcohol on this side, so we know that this must be secondary. And moving on, and here obviously we're going to, using KOH, we're going to use the pore gets poorer rule as we get the Cl and an H, an adjacent H, either on the left or the right side, but the H gets removed from the carbon, which has got the least number of H's. That'll give the major or minor product. And then one of those alkenes undergoes addition to make compound F. Now this seems rather straightforward. The only information that really throws a spanner in the works here is the one that regards D and E. And that is that it cannot exist as geometric isomers. Now there is a little bit of trial and error to get your thinking straight on this, so we'll get started on this. Now the first structure that probably comes to mind for the alcohol would be this. It's a secondary alcohol. It's got the right number of hydrogens. I've got 12 there. And when it gets oxidized to a ketone, which obviously isn't going to react with toluenes or phthalings. And we can treat this as being the chiral carbon in the middle, and we've got one group here, 2 groups there, 3 groups there, and 4 groups here. So yeah, that can exist as an optical isomer. Alright, so if we're to carry on that sequence and do a substitution reaction and the Cl gets substituted in there, this would be compound C in theory. And if we're now going to do an elimination reaction, that means we're going to get a double bond forming here and here. Now it hasn't stated which is major or minor, but the major one would be the one on this side, because this carbon has got the least number of H's on it, whereas this carbon has got the most. So, but we end up with 2 possibilities here. We end up with one, just a minute. Okay, so if we draw these out, we get this as perhaps compound D or E, and this is again just trial error at the moment. And according to the information, these must exist as geometrical isomers. So if we look at this, we'll notice that, well, that is possible for this one. You know, we have an H here and a CH3, and on the other one we're going to have an H and this other group. So we do have different groups on this one. And on this one we have two H's, so obviously that cannot exist. So only one can. So that would make it so there's something wrong with this chain now. So we have to alter this basic alkene we've got here in some way, which means we have to go right back to the start. Now the thing that comes to mind is obviously that we're going to probably have to put a methyl group coming off. This still has to be a secondary alcohol though. Okay, now if we reconsider this, the reason obviously I put the methyl group here is there's a secondary alcohol group there, but if you try and put the methyl group there, it just extends the chain, so it can really only go in one place. So if this undergoes substitution, then what we're going to get is this structure here, which has got the Cl here. Now that means when a double bond forms, it's going to either form here or here. Now let's see when we do that if we can make something which is something that does not have geometrical isomers on either side. Now I've just redrawn those structures here, and so we have the double bond here, and just making sure I've got the right number of H's there. So we have an H here, we have a CH3 here, but we have two CH3s on this, so this cannot exist as a a geometrical isomer, and this one immediately we see the two H's here, we know that one can't as well. So neither of these can exist as geometrical isomers, so that's good, and that means we're on the right track, but we just needed to make sure that the methyl group, or there was a chain and there was a little methyl group coming off that. So that really means we've identified A through E, and we just have to make sure we get F right now. Now having written these out, A is just the secondary alcohol with the side group here, the methyl group, and this is the substituted chlorine on there, and then we do an elimination reaction, and that produces a double bond. Now that's going to either be here or here, and producing this structure up here, which is supposed to be a structural isomer, that means that the Cl in this case is on here, now just taking a proper look at this, the double bond can either be here or here. Now in D and E we're not entirely sure which one it is until we figure out this last piece of information. This has got to be a structural isomer of this, so the Cl in this case, it cannot be here, so it can't be there because that would be the same isomer, so it's got to be different. I've just left the H's off here for now. Now if we had a double bond here, that would mean if we added HCl, the H would add to the carbon which has got the most H's, and that in this case would be this one here, because that would have one H and this would have no H's. In this case, if this was a double bond on this side, then the H would add to this one, because this would have two H's. It would have one here, one there, and it would only have one here. Sorry, I really should have drawn one here. This has no H's because there's 1, 2, 3, 4. Okay, so that would mean that the major product on this one would have the chlorine here, and it would have the H here. Now this is exactly the same as that, so that means this must be the product F with the chlorine here, So that means we have to just swap these two around, and I'll just do that now. Okay, just to reiterate, this is one of the possible alkenes it forms, and this is the other one. The reason this is E is it forms this product here as the major product when HCl is added. When we have HCl, the H is going to go to the carbon which has got the most H's, the rich gets richer, and that means the Cl is going to come into the other side, okay, which is all I've drawn in F. This is supposed to be a structural isomer of this, which it is because the Cl is here on this carbon and not on this one. So these questions can be a little trial and error, but if you're willing to go through them, you should be able to work it.